And that, I think, frees up Mother Nature to tinker around with different sorts of input channels. So I call this the pH model of evolution. And I don't want to get too technical here, but pH stands for potato head. And I use this name to emphasize that all these sensors that we know and love, like our eyes and our ears and our fingertips, these are merely peripheral plug-and-play devices. You stick them in and you're good to go. The brain figures out what to do with the data that comes in. And when you look across the animal kingdom, you find lots of peripheral devices. So snakes have heat pits with which to detect infrared. And the ghost knifefish has electroreceptors. And the star-nosed mole has this appendage with 22 fingers on it with which it feels around and constructs a 3D model of the world. And many birds have magnetite so that they can orient to the magnetic field of the planet. So what this means is that nature doesn't have to continually redesign the brain. Instead, with the principles of brain operation established, all nature has to worry about is designing new peripherals. Okay, so what this means is this. The lesson that surfaces is that there's nothing really special or fundamental about the biology that we come to the table with. It's just what we have inherited from a complex road of evolution. But it's not what we have to stick with. And our best proof of principle of this comes from what's called sensory substitution. And that refers to feeding information into the brain via unusual sensory channels. And the brain just figures out what to do with it. Now, that might sound speculative, but the first paper demonstrating this was published in the journal Nature in 1969. So a scientist named Paul Bach-y-Rita put blind people in a modified dental chair, and he set up a video feed, and he'd put something in front of the camera, and then you would feel that poked into your back with a grid of solenoids. So if you wiggle a coffee cup in front of the camera, you're feeling that in your back. And amazingly, blind people got pretty good at being able to determine what was in front of the camera just by feeling it in the small of their back. Now, there have been many modern incarnations of this. The sonic glasses take a video feed right in front of you and turn that into a sonic landscape. So as things move around and get closer and farther, it sounds like a cacophony. But after several weeks, blind people start getting pretty good at understanding what's in front of them just based on what they're hearing. And it doesn't have to be through the ears. This system uses a electrotactile grid on the forehead. So whatever in front of the video feed, you're feeling it on your forehead. Why the forehead? Because you're not using it for much else. The most modern incarnation is called the brain port. And this is a little electrode grid that sits on your tongue. And the video feed gets turned into these little electrotactile signals. And blind people get so good at using this that they can throw a ball into a basket, or they can navigate complex obstacle courses. They can come to see through their tongue. Now that sounds completely insane, right? But remember, all vision ever is electrochemical signals coursing around in your brain. Your brain doesn't know where the signals come from. It just figures out what to do with them. So my interest in my lab is sensory substitution for the deaf. And this is a project I've undertaken with a graduate student in my lab, Scott Novick, who's spearheading this for his thesis. And here's what we wanted to do. We wanted to make it so that sound from the world gets converted in some way so that a deaf person can understand what is being said. And we wanted to do this, given the power and ubiquity of portable computing. We wanted to make sure that this would run on cell phones and tablets. And also we wanted to make this a wearable, something that you could wear under your clothing. So here's the concept. So as I'm speaking, my sound is getting captured by the tablet, and then it's getting mapped onto a vest that's covered in vibratory motors, just like the motors in your cell phone. So as I'm speaking, the sound is getting translated to a pattern of vibration on the vest. Now, this is not just conceptual. This tablet is transmitting Bluetooth, and I'm wearing the vest right now. So as I'm speaking, the sound is getting translated into dynamic patterns of vibration. I'm feeling the sonic world around me. So we've been testing this with deaf people now, and it turns out that after just a little bit of time, people can start feeling, they can start understanding the language of the vest. So this is Jonathan. He's 37 years old. He has a master's degree. He was born profoundly deaf, which means that there's a part of his Umwelt that's unavailable to him. So we had Jonathan train with the vest for 4 days, 2 hours a day, and here he is on the 5th day.
You.
So Scott says a word, Jonathan feels it on the vest, and he writes it on the board.
Where?
Jonathan's able to translate this complicated pattern of vibrations into an understanding of what's being said.
Touch.
Now, he's not doing this. Jonathan's not doing this consciously because the patterns are too complicated, but his brain is starting to unlock the pattern that allows it to figure out what the data mean. And our expectation is that after wearing this for about 3 months, he will have a direct perceptual experience of hearing, in the same way that when a blind person passes a finger over Braille, the meaning comes directly off the page without any conscious intervention at all. Now, this technology has the potential to be a game changer because the only other solution for deafness is a cochlear implant, and that requires an invasive surgery. And this can be built for 40 times cheaper than a cochlear implant, which opens up this technology globally, even for the poorest countries. Now, we've been very encouraged by our results with sensory substitution, but what we've been thinking a lot about is sensory addition. How can we use a technology like this to add a completely new kind of sense to expand the human Umwelt? For example, could we feed real-time data from the internet directly into somebody's brain, and can they develop a direct perceptual experience? So here's an experiment we're doing in the lab. A subject is feeling a real-time streaming feed from the net of data for 5 seconds. Then 2 buttons appear, and he has to make a choice. He doesn't know what's going on. He makes a choice, and he gets feedback after 1 second. Now, here's the thing. The subject has no idea what all the patterns mean, but we're seeing if he gets better at figuring out which button to press. He doesn't know that what we're feeding is real-time data from the stock market, and he's making buy and sell decisions. And the feedback is telling him whether he did the right thing or not. And what we're seeing is, can we expand the human Umwelt so that he comes to have, after several weeks, a direct perceptual experience of the economic movements of the planet? So we'll report on that later to see how well this goes. Here's another thing we're doing. During the talks this morning, we've been automatically scraping Twitter for the TED 2015 hashtag, and we've been doing sentiment analysis, which means are people using positive words or negative words or neutral. And while this has been going on, I have been feeling this. And so I'm plugged in to the aggregate emotion of thousands of people in real time. And that's a new kind of human experience, because now I can know how everyone's doing and how much you're loving this. It's a bigger experience than a human can normally have. We're also expanding the Umwelt of pilots. So in this case, Vest is streaming 9 different measures from this quadcopter. So pitch and yaw and roll and orientation and heading, and that improves this pilot's ability to fly it. It's essentially like he's extending his skin up there, far away. And that's just the beginning. What we're envisioning is taking a modern cockpit full of gauges And instead of trying to read the whole thing, you feel it. We live in a world of information now, and there's a difference between accessing big data and experiencing it. So I think there's really no end to the possibilities on the horizon for human expansion. Just imagine an astronaut being able to feel the overall health of the International Space Station. Or for that matter, having you feel the invisible states of your own health, like your blood sugar and the state of your microbiome, or having 360-degree vision, or seeing in infrared or ultraviolet. So the key is this: as we move into the future, we're going to increasingly be able to choose our own peripheral devices. We no longer have to wait for Mother Nature's sensory gifts on her timescales. But instead, like any good parent, she's given us the tools that we need to go out and define our own trajectory. So the question now is, how do you want to go out and experience your universe? Thank you.
Did you feel it?
Yeah. Actually, this is the first time I felt applause on the vest. It's nice. It's like a massage.
Twitter's going crazy. Twitter's going mad. So stock market experiment. This could be the first experiment that kind of secures its funding forevermore, right? If successful.
Well, that's right. I wouldn't have to work at NIH anymore.
Just to be skeptical for a minute, I mean, this is amazing, but isn't most of the evidence so far that sensory substitution works, not necessarily that sensory addition works? I mean, isn't it possible that the blind person can see through their tongue because they already have the visual cortex is still there, ready to process, and that is needed as part of it?
This is a great question. We actually have no idea what the theoretical limits are of what kind of data the brain can take in. The general story, though, is that it's extraordinarily flexible. So when a person goes blind, what we used to call their visual cortex gets taken over by other things, by touch, by hearing, by vocabulary. So what that tells us is that the cortex is kind of a one-trick pony. It just runs certain kind of computations on things. And when we look around at things like Braille, for example, people are getting information through bumps on their fingers. So I don't think we have any reason to think that there's a theoretical limit that we know the edge of.
If this checks out, you're going to be deluged by, I mean, there are so many possible applications for this. Are you ready for this? What are you most excited about?
Yeah.
The direction it might go.
I mean, I think there's a lot of applications here in terms of beyond sensory substitution. The things I started mentioning about astronauts on the space station, they spend a lot of their time monitoring things, and they could instead just get what's going on, because what this is really good for is multidimensional data. The key is this: our visual systems are good at detecting blobs and edges, but they're really bad at what our world has become, which is screens with lots and lots of data. We have to crawl that with our attentional systems. So this is a way of just feeling the state of something, just like the way you know the state of your body as you're standing around. So I think heavy machinery, safety, feeling the state of a factory, of your equipment, that's one place it'll go right away.
David Eagleman, that was one mind-blowing talk. Thank you very much.
Chris.
I want to start by telling you a little story. Come with me on a journey into the past and how that kind of paved the way for a new genetic future. When I was about 8 years old, the King Tutankhamun exhibit, the famous Egyptian king, toured the world for the first time. And I had the opportunity to travel with my family. I grew up in Texas. We traveled to New Orleans in Louisiana, and stood outside in weather very much like weather out there today, in the rain, waiting for several hours for our turn to go in and see these incredible treasures. And I was absolutely blown away. The funerary mask, the chariots. It was like seeing objects that could have been made 2 weeks before, but they were 3,500 years old. And that instilled in me a fascination with the past that's continued to the present day. I started to devour every book I could, not only on ancient Egypt, but Greece, Rome. I started to expand outward, the history of Asia, Africa, and the Americas. And ultimately, of course, started to ask deeper questions about the history of humans. We are taught in school, many of us, that history really starts around 1500. We memorize all of the kings and the acts and so on, but we forget about all the tens of thousands of years of human history that came before that. And that really is what I've devoted my career to, understanding the deeper aspects of human history, really trying to explain the patterns of human diversity that we see around the world today. We're so diverse as a species. You travel, you walk down the street in a major city, you see people who seem to be so different from each other and from ourselves. How did those differences arise? And how did we scatter to the wind to populate the entire planet? That's really what I focused my career on. Well, historically, to approach these issues, to understand human diversity and human origins, ultimately is what we're talking about, we would have gone out and dug things up out of the ground. So the study of paleoanthropology and archaeology, digging often skeletons from the ground in, say, East Africa, and guessing on the basis of the morphology of these, often skull shape, this is more likely to be the missing link than that is. But as a geneticist, I was never really satisfied with this because there's so little actual data in paleoanthropology. It gives us lots of fascinating possibilities about our origins, but it doesn't give us the probabilities about direct lines of descent that I, as a budding young scientist, really wanted. Data-driven results. How do we study human origins and human migration patterns for tens of thousands of years using a handful of finds that are often very arbitrary and due to chance? Well, as I was mulling over what I was going to do with my career, starting university in the mid-1980s, the field of genetics was undergoing a revolution. And we were just beginning to understand the structure of DNA. DNA sequencing had been invented just a few years before, in the late 1970s. Fred Sanger, Wally Gilbert, and his colleagues had developed methods of actually determining the sequence of all of the A's, C's, G's, and T's in a genome. Initially viruses, later on it would be bacteria. But the goal, of course, everyone was thinking about was sequencing the human genome. And that was what excited me the most. DNA is a long linear molecule, the double helix we've all heard about, described by Watson and Crick in 1953, composed of billions of these subunits, A's, C's, G's, and T's, the blueprint to make another version of you. And as the DNA is being replicated or copied to be passed on in every generation, occasionally typos occur, like copying long text by hand. You'll misincorporate an I for an E, or in the case of DNA, a C for a G. These mutations, as we call them, become markers of descent. And if we share genetic markers, a change in the DNA, with another person, it means we share an ancestor in the past who first had that typo as they were copying their genome and passing it on to the next generation. By studying these markers, we decided we might be able to say something about human origins and help to explain patterns of human diversity around the world. So again, that is really what I've spent my career studying. It's an extraordinary story. If we go back to Charles Darwin, he, for instance, guessed that humans ultimately had origin in Africa, in common with all of the other great apes, because he posited chimps and gorillas look more like us than other species. They live there, so we probably came from there. But what about us as a species, not just us as great apes? Where did we come from? Well, that really took DNA to be able to solve. And the story that emerged was a shocking one at first. I was just showing one of my millennial employees the cover of Newsweek story was we all trace back to an African ancestor within the last 200,000 years. And perhaps even more shockingly, it's only in the last 60,000 years that we've scattered to the winds, leaving Africa to populate the entire world. That's only about 2,000 human generations. It's the blink of an eye in an evolutionary sense. So in only 2,000 human generations, we've generated the majority of this diversity that distinguishes us today. We're much more closely related than we ever suspected before we started studying the A's, C's, G's, and T's in the human genome. Well, it was with this in mind, this obsession, armed with the new tools of genomics that were coming along in the late 1990s and early aughts, that we launched the Genographic Project 14 years ago, last month, April 13th, 2005. I stepped out on stage, National Geographic headquarters in Washington, D.C., to announce this project to the world. IBM is our partner. It was a $40 million project, very big science for the time. The initial human genome had just been completed, in quotes, because of course we're still in the process of completing it in reality. But as I was stepping out onto stage, the then CEO of National Geographic pulled me aside 10 minutes before I walked out on stage, and he said, "Spencer, we're very excited about this project. The science is so cool. We think we're going to discover so many amazing new things. But this aspect of the project where you're going to be selling DNA testing kits to members of the general public, no one's done that before. We have no idea what the interest will be. But I know consumer behavior, and I got to tell you, no one's going to spend $100 to test their own DNA. If you sell 1,000 of these in the next few years, you'll be lucky. So really focus on the science, soft pedal the whole DNA testing thing." And I said, "Okay, John," my name is John Fahey, "you're on." So walked down on stage, announced it, and we sold 10,000 of those kits on the first day. We had 100,000 by the end of that year, 7 months later, and suddenly a new industry was born, the industry of consumer genomics, which has taken off. Really over the last few years. The companies you might have heard of were created in the wake of that initial success. So again, we launched in 2005, 23andMe, one of the big players now, came out in 2007. Ancestry, which is the dominant player, launched their products in 2012. And it's coincided with a really interesting pattern. So if you think back to me starting graduate school in 1989, this debate about whether it's theoretically possible to sequence the billions of nucleotides in the human genome, it took 15 years throughout the whole process of the Human Genome Project, up until about 2001 or so, to sequence one human genome at a cost of $3 billion. So $3 billion, 15 years. Well, the cost of sequencing additional genomes, of course, reduced over time, because once you have a scaffold to layer the segments of the newly sequenced genomes onto, it gets much easier. And it essentially followed Moore's law, the law from computing that says that computer chips are going to roughly double in power every 18 to 24 months. And then something happened in 2007, something we called next generation sequencing. And I won't go into detail on what that is, but it effectively involves miniaturizing the process, doing it in parallel, billions of reactions going on at a time, microfluidics, et cetera, et cetera. But what that enabled was a sea change in the technology and our ability to sequence genomes. DNA sequencing technology is the most rapidly evolving technology in human history. It has fallen off a cliff. And as you can see from this curve, the cost of sequencing genomes has dropped essentially to zero. It's essentially free compared to that first genome. At least. And when things become free, they become ubiquitous. And so what's happened over the last few years in the consumer genomics industry, and this is the US largely, but it's starting to happen in Europe as well, is that the number of people testing has skyrocketed. So at the end of last year, 26 million people in the US had tested their DNA with a consumer testing kit. We're up over 30 million now. These numbers have been doubling for the last 2 years. So we estimate by the end of 2019, we'll be at 50 million. By the end of 2020, we'll be at 100 million. That's a lot of people. Even at 30 million, though, that's 10% roughly of the US population. Now, what people don't realize is that, of course, because we get our genomes from our parents and our grandparents and we pass them on to our children and so on, we share our DNA with a huge cloud of other people out there. And so when we test our own genomes, we're testing the genomes of all of the people that we're related to, out to relatively distant levels of relatedness. Now, if you look at these two curves, the way the cost is dropping and the adoption is going up at an exponential rate, the prediction is, of course, in the future, we will all be sequenced. And this is the vision. I've predicted, other people have talked about this, that within 5 to 10 years, every child in the developed world will have their genome sequenced at birth, possibly even before, because you can do it non-invasively by drawing the mother's blood now. So in the future, your genomic data will become part of the data cloud that we all carry around with us, just like our credit history or our social media profiles, all of the data that helps us define who we are, helps us to make decisions about our lives. And occasionally, when we let people in, allows them to make decisions about us. So this is the grand vision that we were espousing a year ago. And then things started to change in the world of technology. As they famously say, if you're using a product that is feature-packed and it's free and you wonder, how did they do this for free? You are the product. As we began to discover last year, your data is being used by these large corporations to fund what you're seeing on the front end. And believe me, if you've ever seen Facebook on the back end from an advertiser perspective, it's a very different beast. It's a lot more like a spreadsheet than a nice graphical user interface. So this started to come out last year. People, of course, had known this for a while if you were in the industry, but I think the general public only began to realize this last year. The same thing began to happen in the consumer genomics business. Genealogy sites allowing the FBI, in this case, to go in and catch a killer from back in the 1970s and 1980s. The case had gone cold, but using the size of these genealogy databases and looking at the intersection of cousins, you were effectively able to triangulate down to particular individuals, start catching criminals. An inkling that although people may be testing for genealogical purposes, they were in effect creating a huge national DNA database inadvertently, and they were paying for it themselves, which is kind of interesting. These stories continue to come out this year. Companies selling access to the FBI genomic databases without informing the customers. Bloomberg, stories about no one is safeguarding your DNA, the CRISPR babies in China that we've all heard about. And interestingly, China using genetic technologies to profile a minority in Xinjiang in the western part of the country. These are incredibly powerful technologies. And when incredibly powerful technologies become really inexpensive, they're very easy to misuse. And so people in the last few months have been asking a lot of questions about genomics. I would argue that perhaps the most disruptive technologies of the first half of the 21st century are artificial intelligence, AI, and genomics. AI is going to have a huge impact on society, the nature of work, social relationships, potentially governments, potentially entire economies. Genomics, though, will have an intensely important impact on us as individuals at a very personal level. So not only will we use genomics to understand who we are in the present and a little bit about our past, but we'll begin to make decisions using these relatively inexpensive and more ubiquitous technologies to make decisions about our children, grandchildren, and so on in the future. And with all of this in mind, we have recently formed an institute, the world's first institute, to look into policy and ethical issues focused specifically on personal genomics. So this is not genomics that you might have done in consultation with your physician in the doctor's office. We're really not focusing on the disease side of things. It's more about these questions of identity and how these simple decisions where you spend $60, $70, $80 or euros on a personal DNA testing kit could have, vastly different knock-on effects than you ever suspected when you spit into that tube and send it off. So we'll be announcing this next month, but I wanted to give you a sneak preview of what we're focusing on. But the issue of genomic identity and privacy is the very first issue that we think is, the thing that we're going to focus on initially. Thank you very much.
So by a show of hands, how many people here have heard of the ultra deep field experiment by the Hubble telescope? Okay, very few. Okay, well, strap in because I'm glad I get to tell you about this. What happened some years ago was that NASA had completed a low-resolution map of the night sky, and they decided that they wanted to go deeper. So they picked a little tiny patch of space, that's about the size of a pencil tip at arm's length. And it was black. There was nothing there. And what they decided they would do is point the finely honed lens of the Hubble telescope at that little patch of space. So every time the Hubble came around the Earth, they pointed the telescope at that little patch to see if they could capture any photons and see if there was actually something in there that was too dim to see normally. So every time the Hubble came around the Earth, they pointed it for 20 minutes, and they pulled this trick off 400 times. And at the end of that, they compiled all the information, they collected all the lonely photons that had trickled in from distant reaches of the universe, and they put it together, and they found that there was something in that little patch of space after all. And it wasn't a star, and it wasn't a cluster of stars. It was 10,000 galaxies. Now, a galaxy is 100 billion stars. So we're talking 1,000 trillion stars in this little patch of space. Each one of those stars, just like our sun, many of them presumably with planetary systems around them, all of them with the potential to house unknown forms of biology, right? So I think this is a good consciousness raiser to think about the size of the mysteries that surround us. So I am a scientist. I've devoted my entire life to science because I figure if we want to understand what's going on in this strange world around us, there's probably no better method than to directly study the blueprints. And science in the last 400 years has been tremendously successful. We have cured smallpox and polio and gotten men to the moon and made the internet and tripled lifespans. But I think what you really get from a life in science is this knowledge that after you walk the pier of everything that we know in science, at some point you reach the end of the pier. And beyond the end is everything that we don't know. It's all the uncharted waters, the deep mysteries that we don't have insight into yet, like why mass and energy are equivalent, or what dark matter and dark energy are, or why there are multiple spatial dimensions, or how you build consciousness from mechanical pieces and parts. That's the real lesson that you get from science, is about the vastness of our ignorance. Now, I have no doubt that every generation we will continue to add a few more slats to the pier, but it's a huge ocean, and we don't really have any guarantee how far we'll get. And certainly in our brief twinkling of a 21st century lifetime, we're not going to get to the end of that. And so the lesson that you get from science is that what we know is so vastly outstripped by what we don't know. So given that situation, I have been interested in what has happened this last decade with the books by the neo-atheists. And these books are some of my favorite books, and they're very important and insightful books. But what's been interesting to me is the public reaction to them, because what they have led to, as far as I can see, is something of a misconception widely, that scientists don't have the capacity to gamble beyond the available data. And that scientists are acting as though we've got it all figured out. We understand it, F equals ma, E equals mc squared. We can put in equations, or if we can't yet, then we're pretty close, and it should suffice to capture a description of the whole cosmos. I think that's actually not a very good description of how science actually operates. Ben's right when he said that science is about disproving other people's hypotheses, but it's about so much more than that. Science is really about this creativity of making up new hypotheses. And there's a part of the scientific temperament is this tolerance for holding multiple hypotheses in mind at the same time. Now, what we actually do is we make up new stories in the laboratory every day, and then we go and we seek evidence. We gather evidence to weigh in favor of some stories over others. But it's often the case that some questions are too far out right now. They're beyond the toolbox of science, and as a result, we're unable to gather evidence for them. And in that situation, it's okay. Science is comfortable holding multiple hypotheses on the table. That ambiguity is accepted as part of the relationship we have with Mother Nature. It's part of the vast mysteries around us. We have to have that ambiguity. So I don't pretend like we've got it all figured out. And as a result, I have felt sometimes that perhaps we know too little to commit to a position of strict atheism. Now, at the other end of the spectrum, we know way too much to commit to any particular religious story, right? So there are 2,000 religions on the globe, and it's been pointed out by others that everyone already knows what it's like to be an atheist, because all you need to do is look at someone else's religion and you say, well, that's patently ridiculous that you would believe in that. And of course, they're looking back at you and thinking the same thing. So whenever I'm sitting next to somebody on an airplane, I ask everybody if they've ever heard of the ultra deep field experiment by the Hubble telescope. So far, nobody's heard of that, but everybody's able to tell me all of the details of whatever cultural story they grew up on. And you don't need to be an anthropologist to recognize that our nervous systems absorb whatever our cultures pour into us. So if you grow up in Saudi Arabia, you're going to love Islam. And if you're born in Rome, you'll love Catholicism, and Tel Aviv Judaism, and Springfield, Ohio Protestantism. And it's not a coincidence that there's not a blossoming of Islam in Springfield, Ohio, and there's not a blossoming of Protestantism in Mecca. It's because we're products of our culture. We accept whatever is poured into us, right? If there were one truth, you would expect that it would spread everywhere evenly, but clearly the data doesn't support that. The crazy part is our cultures pour the stuff into us, and then sometimes people are willing to fight and die over the particular stories. Ralph Waldo Emerson pointed out a while ago that the religious stories of one generation become the literary entertainment of the next generation. And you can see that nobody's fighting over Isis and Osiris anymore, or the Greek and Roman panoplies, not so much. And so I want to give you an example of this. I don't know if any of you are familiar with the creation story of the Bakuba kingdom in the Congo, but their creation story goes like this. There was a white giant named Mombo who had a sharp pain in his belly, and he vomited up the earth and the sun and the moon and the stars. I'm not making this up. And then he had a second pain, and he vomited up the animals and people and trees. And included in that second ejection was, and I quote, the leopard, the anvil, the eagle, woman, the monkey fumu, firmament, medicine, man, and lightning. Now, if you find the creation story of the Bakuba an unlikely explanation for how we got here, just keep in mind that if you were Bakuba, you would find equally bizarre the Western story of the naked couple and the talking reptile and the prohibited produce. And if you were Bakuba living in Kansas, you would be fighting to get this in your children's textbooks. Now, I'm not suggesting that the Bakuba story is wrong or the Adam and Eve story are wrong because there are competing stories. I'm suggesting they're wrong because all the available evidence we can gather weighs against them. So, for example, the biblical story suggests that the earth is 6,000 years old. Our best science tells us that it's 4.5 billion years old. So that means the biblical account has to somehow explain how the Japanese were making pottery 4,000 years before the earth existed. So for my money, this puts me somewhere in the middle. I have felt for a long time that we know too little to commit to strict atheism, and we know far too much to commit to a particular religious story. So what has surprised me is the amount of certainty that I find out there. So when you walk into a bookstore, what you find are the books by the neo-atheists and the books by the fundamentally religious, and they argue with each other and they polarize each other, and they're spending all of their energies on that. And it has felt to me for a while like maybe there should be another voice here, because that seems too limited for a modern discussion. Because if you think about the space of possibilities, right? So take the whole Judeo-Christian Islamic tradition, that's one point in the possibility space. Take the Eastern religions, that's another point. Take the idea that we're mechanical pieces and parts and we shut off when we die, that's another point. We were planted here by space aliens, take another point, right? When you start populating the space, what you realize is there are vast landscapes in between of possibilities, and all of these points are infinitesimally unlikely, right? But together they add up to this possibility space, and I feel like there's not really enough discussion about that space. Instead, the whole discussion has been limited to what I consider perhaps a false dichotomy, this God versus no God, and that's where the conversation has ended. Now, some people in the middle position, sometimes people use the term agnostic. I don't use that term because the way I see it used, it typically is used as a weak term. Often when people say they're agnostic, what they mean is, I'm not sure whether the guy with the beard on the cloud exists or doesn't exist, right? So I don't call myself an agnostic. I call myself a possibilian. And the idea with possibilianism is an active exploration of new ideas and a comfort with the scientific temperament of creativity and holding multiple hypotheses in mind. So possibilianism is now 18 months old. And I first announced it when I was on a live national interview on NPR. I explained it and I defined it. And when I got done with the interview, I got back in my truck and I drove over to my laboratory at Baylor College of Medicine, where I'm a neuroscientist. And I settled in for a day of work and I opened up my email and I had hundreds of emails from people. And they all said, hey, I think I'm a possibilian too. So I thought that was pretty cool. So I Googled the word and it turns out the word didn't exist. There were 0 hits. So I did what anybody would do. I bought possibilian.com. And then I waited to see what would happen. Well, what happened has been amazing. What happened is groups started popping up all over the place. On Facebook, possibilian groups got started. The New York Times did an article on it. MSNBC did an article on it. It spread worldwide. The Uganda Times just had a beautiful piece on possibilianism. The India Sunday Times. There are now 15,000 Google hits. And it's really caught fire. One thing I noticed that was funny is people who had heard about it on the radio didn't always know how to spell it, or they forgot the name, and so people started calling it possibilitarian also, and all kinds of things, and spelling it every way you can imagine. And I thought, you know what? That's perfect. That's right in the possibilian spirit. Spell it however you want to do it. But the question I started wondering about is why? What is the reason that this movement is catching on, given that it's a very strange movement in that we don't subscribe to anything? So it struck me that maybe what's going on, now that we've passed the first decade of this millennium, I think maybe people are a little bit tired of people acting as though they're certain about things that they can't possibly be certain about. So they're a little tired of the debates between Dawkins versus the Discovery Institute. And as Voltaire said, uncertainty is an uncomfortable position, but certainty is an absurd position. So I want to make 2 points of clarification about possibilianism. So one is, sometimes people come up to me after a talk and they say, that's terrific that you're a possibilian, and I'm so glad that anything goes in possibilianism because that means you get me in terms of ESP and crystals and whatever. No. Possibilianism is not anything goes. It's anything goes at first. And then we import the tools of science to rule out parts of the possibility space. So it would be terrific if ESP existed. We would all love that. But to the extent that we can measure things now, we cannot find any evidence to support it. And so the idea is you import the tools to sculpt, to structure the possibility space. You can rule out whole areas. And the interesting part of possibilianism really picks up where the toolbox of science leaves out. It's where we no longer have the tools to address it, and we have to understand the space of possibilities. That's where it's really important. And the reason it is so important to keep that open-mindedness about all the parts we don't know is because we know for certain about the magnitude of things that we don't know. So in every generation of scientists, people have always felt that they have all the pieces and parts that they need in order to answer what's going on around them in the cosmos. But just imagine trying to explain the northern lights in the absence of understanding the magnetosphere, or trying to explain the heart before the concept of a pump was invented, or trying to understand how muscles work before electricity is discovered. You would make theories, but you would be doomed to be incorrect. Well, we're in that same position now. So we've got Newtonian physics and Einsteinian physics and quantum mechanics, and we think, okay, we've sort of got all the pieces and parts. But on the one hand, there's all the unknown unknowns, all the stuff we don't even know we don't know. But what I want to emphasize is all the stuff that we know for sure we don't know. So take something like dark matter, right? So astrophysicists
look at the movement of the planets and the galaxies, and they look at how everything's moving around, and they look at the gravitational pull. And what they realize is something's missing. There's something out there that we can't quite see or smell or touch, but it must be there to make the equations work out, to make the movements in the cosmos explain. And so we're going to call this a fudge factor, and we're going to call it dark matter. And the idea is that dark matter is the thing that we don't exactly know what it is, but we require it to make the equations work out. Okay. Some of you may already know, dark matter is not a tiny fudge factor. 90% of the known universe is what we call dark matter. That's a lot to sweep under the rug. Okay, and this is what I study. I go in the lab every day and study the human brain. This is the most complicated device we have ever found in the universe. It's essentially an alien kind of computational material. And it is so dense in its connectivity that if you were to take a cubic millimeter of brain tissue, there are more connections in there than there are stars in the Milky Way galaxy. So this is incredibly complex. And yet somehow this wet mechanical network system here is you. It's all your hopes and dreams and aspirations, right? Somehow that's you. If you were to lose a little part of your pinky, you wouldn't be any different. But if you lose an equivalently sized piece of neural tissue, that completely changes your conscious state, right? Well, the problem is we don't know how to take mechanical pieces and parts and build private subjective experience out of that. Imagine that I gave you 1 trillion Tinker toys and I said, okay, hook it up. So this is a lever and this touches that and that causes that and so on. At what point do you add one more Tinker toy and then you say, it's experiencing the taste of feta cheese now? Right, that's the problem. We don't know, we don't have any way to take our equations and say, okay, we'll just carry the 2 and do a triple integral, and then that's, that's feta cheese, or that's the redness of red, or the qualia of pain, or something. We don't, not only do we not have a theory of how the brain works, we don't even know what such a theory would look like. Okay, so all of this calls for a bit of intellectual humility. Now, I was giving this talk recently, and somebody came up to me afterwards and said, hey, Dr. Eagleman, good job on the talk. He said, you know what? I think you should become a politician because you're unwilling to commit to anything. And he said to me, why don't you just cowboy up and commit to something? So I thought about that. So in Texas, where I come from, we have this lovely expression, to cowboy up. And what it means is to firmly commit to a decision. And we really value this trait in people. We like people who can firmly commit to a decision. So if you're trying to decide, should I take the cattle out in the rain, or should I marry this woman, or should I sell the ranch? We like people who can make a really firm decision. But what I'm going to suggest is that there are some domains where it's appropriate to cowboy up, and there are some domains where it's not so appropriate. So would you stop a guy on a ranch and say, tell me if you think there are extraterrestrial civilizations? Do you care what his opinion is? Would you value it more than, say, an astrobiologist? And if you wouldn't ask him about extraterrestrial civilizations, that suggests that there are some domains in which it is not appropriate to commit and act like you know the answer in the absence of having good evidence. So the next time someone says to you to cowboy up and commit to a decision, I suggest that you tell them, no, I would rather geek out. And the idea of geeking out is having a creativity for new narratives and a comfort level with holding multiple possibilities in mind. And you should feel free to cite the gospel of science, the most important 3 words that science ever gave to humankind. So my message to you is this: when you leave here and you go back out into this strange world, try to seek comfort with having multiple narratives and uncertainty. And this is not just a plea for simple open-mindedness, but for an active exploration of new ideas. I think this is important for our education, for our legislation, for perhaps the future of our warfare. So when you leave Pop Tech full of ideas, go back and look around the strange world you're in and see if you can live a life that is free from dogma and full of awe and wonder, and see if you can celebrate possibility and praise uncertainty. Thank you very much.
So I have a feature on my website where every week people submit hypothetical questions for me to answer. And I try to answer them using math, science, and comics. So for example, one person asked, what would happen if you tried to hit a baseball pitched at 90% of the speed of light? So I did some calculations. Now, normally when an object flies through the air will flow around the object. But in this case, the ball would be going so fast that the air molecules wouldn't have time to move out of the way. The ball would smash right into and through them. And the collisions with these air molecules would knock away the nitrogen and carbon and hydrogen from the ball, fragmenting it off into tiny particles, and also triggering waves of thermonuclear fusion in the air around it. This would result in a flood of X-rays that would spread out in a bubble along with exotic particles, plasma inside, centered on the pitcher's mound. And that would move away from the pitcher's mound slightly faster than the ball. Now, at this point, about 30 nanoseconds in, the home plate is far enough away that light hasn't had time to reach it, which means the batter still sees the pitcher about to throw and has no idea that anything is wrong. Now, after 70 nanoseconds, the ball will reach home plate, or at least the cloud of expanding plasma that used to be the ball. And it will engulf the bat and the batter and the plate and the catcher and the umpire and start disintegrating them all as it also starts to carry them backward through the backstop, which also starts to disintegrate. So if you were watching this whole thing from a hill, ideally far away, what you'd see is a bright flash of light that would fade over a few seconds, followed by a blast wave spreading out, shredding trees and houses as it moves away from the stadium, and then eventually a mushroom cloud rising up over the ruined city. So the Major League Baseball rules are a little bit hazy, but under rules 6.02 and 5.09, I think that in this situation, the batter would be considered hit by pitch and would be eligible to take first base if it still existed. So this is the kind of question I answer, and I get people writing in with a lot of other strange questions. I've had someone write and say, scientifically speaking, what is the best and fastest way to hide a body? Can you do this one soon? And I had someone write in. I've had people write in about, can you prove whether or not you can find love again after your heart's broken? And I've had people send in what are clearly homework questions they're trying to get me to do for them. But one week, a couple months ago, I got a question that was actually about Google. If all digital data in the world were stored on punch cards, how big would Google's data warehouse be? Now, Google's pretty secretive about their operations, so no one really knows how much data Google has. And in fact, no one really knows how many data centers Google has, except people at Google itself. And I've met them a few times, tried asking them, and they aren't revealing anything. So I decided to try to figure this out myself. There are a few things that I looked at here. I started with money. Google has to reveal how much they spend in general, and that lets you put some caps on how much, how many data centers could they be building, because a big data center costs a certain amount of money. And you can also then put a cap on how much of the world hard drive market are they taking up, which turns out it's pretty sizable. I've read a calculation at one point. I think Google has a drive failure about every minute or two, and they just throw out the hard drive and swap in a new one. So they go through a huge number of them. And so by looking at money, you can get an idea of how many of these centers they have. You can also look at power. You can look at how much electricity they need, because you need a certain amount of electricity to run servers, and Google is more efficient than most, but they still have some basic requirements, and that lets you put a limit on the number of servers that they have. You can also look at square footage and see how many, of the data centers that how big are they? How much room is that? How many server racks could you fit in there? And for some data centers, you might get two of these pieces of information. You know how much they spent, and you also say, because they had to contract with a local government to get the power provided, you might know what they made a deal to buy, so you know how much power it takes. And then you can look at the ratios of those numbers and figure out, for a data center where you don't have that information, you can figure out, but maybe you only have one of those, the square footage, then you could figure out, well, maybe the power is proportional. And you can do the same thing with a lot of different quantities, with guesses about the total amount of storage, the number of servers, the number of drives per server. And in each case, using what you know to come up with a model that narrows down your guesses for the things that you don't know, sort of circling around the number you're trying to get. And this is a lot of fun. The math is not all that advanced. And really it's like nothing more than solving a Sudoku puzzle. And so what I did, I went through all of this information, spent a day or two researching, and there are some things I didn't look at. You could always look at the Google recruitment messages that they post. That gives you an idea of where they have people. Sometimes when people visit a data center, they'll take a cell cam photo and post it, and they aren't supposed to, but you can learn things about their hardware that way. And in fact, you can just look at pizza delivery drivers. Turns out they know where all the Google data centers are, at least the ones that have people in them. But I came up with my estimate, which I felt pretty good about, that was about 10 exabytes of data across all of Google's operations. And then another maybe 5 exabytes or so of offline storage in like tape drives, which it turns out Google is about the world's largest consumer of. So I came up with this estimate, and this is a staggering amount of data. It's quite a bit more than any other organization in the world has, as far as we know. There's a couple other contenders, especially everyone always thinks of the NSA. But using some of these same methods, we can look at the NSA's data centers and figure out, we don't know what's going on there, but it's pretty clear that their operation is not the size of Google's. Adding all of this up, I came up with the other thing that we can answer, which is, how many punch cards would this take? And so a punch card can hold about 80 characters, and you can fit about 2,000 or so cards into a box. And you put them in, say, my home region of New England, it would cover the entire region up to a depth of a little less than 5 kilometers, which is about 3 times deeper than the glaciers during the last ice age, about 20,000 years ago. So this is impractical, but I think that's that's about the best answer I could come up with. And I posted it on my website. I wrote it up. And I didn't expect to get an answer from Google. Because, of course, they've been so secretive. They didn't answer any of my questions. And so I just put it up and said, well, I guess we'll never know. But then a little while later, I got a message a couple weeks later from Google saying, hey, someone here has an envelope for you. So I go and get it, open it up, and it's punch cards. Google branded punch cards. And on these punch cards, there are a bunch of holes, and I said, thank you. And I was, okay, so what's on here? So I get some software and start reading it and scan them, and it turns out it's a puzzle. There's a bunch of code, and I get some friends to help, and we crack the code, and then inside that is another code, and then there's some equations, and then we solve those equations, and then finally, and out pops a message from Google, which is their official answer to my article, and it said, no comment. So, and I love calculating these kinds of things. And it's not that I love doing the math. I do a lot of math, but I don't really like math for its own sake. What I love is that it lets you take some things that you know, and just by doing these, moving symbols around on a piece of paper, find out something that you didn't know that's very surprising. And I have a lot of stupid questions, and I love that math gives the power to answer them sometimes. And sometimes not. This is a question I got from a reader, an anonymous reader, and the subject line just said urgent, and this was the entire email. If people had wheels and could fly, how would we differentiate them from airplanes? Urgent. And I think there are some questions that math just cannot answer. Thank you.
Let's give it up for Randall. All right.
Hi. All right. So I wrote a book. It's full of my answers to questions that people submitted through my website. And so one of the questions that was submitted that I would like to talk about today is the question that someone asked, what if you built a periodic table using bricks where each brick was made from the corresponding element. And so there's a bunch of different elements, some of which are easier or harder to get a hold of. All in all, there are of the 118 elements in the periodic table, there's about 30 of them which you can get at the local supermarket. You can get samples of aluminum. You can get samples of oxygen and nitrogen are not hard to find either. And then there are another bunch of elements that you can get if you're a little bit more creative. For example, if you need a radioactive source for a cloud chamber, which is like a science project you can do, you can take apart a smoke detector because they'll have like a tiny lump of americium in the middle of it. And if it's a very small amount, but if you wanted to make a brick, and you could just buy a whole bunch of smoke detectors and disassemble them all and gather all the americium together. And this is an effective way to get a brick-sized sample of a rare element that's otherwise hard to find, and B, get yourself onto a bunch of government watch lists really quickly. But despite so there's some dangers to this, which is, for example, a lot of these elements, in addition to being maybe hard to find and or some degree of illegal, some of them are kind of dangerous to handle. So mercury, depending on what form it's in, can cause mercury poisoning, which is really bad. Even some of the elements up near the top of the table, like beryllium, is I've heard that it's not not radioactive or anything, but you don't want to get it on your hands and into your food. So but despite this, people try to collect samples of as many elements as they can. And I totally understand this this sort of collector's compulsion that people have, because I played the original Pokemon on Game Boy, and if you look up what year I was born and sort of the release dates and when Pokemon Blue and Gold came out, you'll realize that I was actually not quite in the I was a little older than the demographic that was supposed to be playing Pokemon. But I played through and there's the appealing idea that there's originally 151 plus or minus Pokemon that the goal is to collect them all. And so there are 118 elements. So it's easy to think of them as sort of radioactive and sometimes very short-lived Pokemon. But people who try to collect them usually top out somewhere around 80 to 90, depending on how comfortable you are with your health and safety, how much money you have to put into this, and in the case of plutonium, how many international laws you're willing to violate. But and the elements at the very bottom of the table are the ones that they will that they typically have a hard time with for reasons which will become clear in a moment. So we're going to start with the top of the table. So what I decided to do is think, okay, if I'm going to build a periodic table, there's going to be trouble near the bottom, but let's start with the top. So the first row of the periodic table is just hydrogen and helium. And that would be easy to build because you get a bunch of hydrogen, get a bunch of helium. I think we have a helium shortage, but you can still buy it at party stores. And so if you made a brick of those, it would be really anticlimactic. It would just sort of diffuse and float away. But this would be a good place to stop. Because we have 7 rows to build. So of these rows, the first 2 rows really you can build without too much trouble. The 3rd row will burn you with fire. The 4th row will choke you with toxic smoke. The 5th row will do all of the things that the first rows did, plus give you a mild dose of radiation. The 6th row will disintegrate instantly in a column of steam and extremely toxic dust and smoke and destroy whatever building you're doing this in. And you should not build the 7th row. But, so the first two rows are okay. You can build these without trouble. The second row, you also, if you built this, it would, again, you'd have some elements that are solid and some that are gases, but they would basically float away. The one though that I sort of want to point out here is fluorine. Fluorine is really, I think, the worst element. It's the most reactive element in the periodic table. And I was recently reading a list of chemists who have been mauled or killed doing fluorine experiments. So not only is it's super reactive, so there's a fluorine compound, which if you have a gas of this compound and you place things in it, almost any substance will spontaneously catch fire in a fluorine atmosphere, including for one of these compounds, ice cubes. So it's also, so you don't want to breathe it in. It would just sort of spread out across the ground, but you can back away slowly. I do remember seeing in a data sheet that it will also eat through many common gas mask materials. So, be careful with your safety equipment. But it really doesn't, become a scary situation until we get to the third row. So the third row has a couple of troublemakers. Over on the left is phosphorus, or over on the left is sodium and magnesium. And those would probably also, you can see the sodium actually, I think I drew it starting to tarnish a little bit, depending on how moist the air is and what the conditions are like. Those would more or less rapidly start to oxidize, either slowly or quickly. But over on the right, we have phosphorus. And because it's, I guess, more fun to draw, I assumed that we are using the white allotrope of phosphorus, which is will spontaneously ignite when it comes into contact with air. And so we have this lump of burning phosphorus, and then the things around it, which might not normally spontaneously catch fire, will be lit on fire by the phosphorus. And as if the whole situation were not combustible enough, it's not just happening in oxygen, because we've got fluorine from the row before spreading out over it. And then also we have chlorine that's just below the fluorine, which is almost as bad. So at this point, you definitely don't want to breathe this in. You want to back away. It's going to be a lot more smoky than the previous one, but you could probably survive this. The fourth row gets trickier. So the fourth row introduces a bunch of new elements, including the metals, a lot of the more traditional metals, and it's also, we have a lump underneath the phosphorus is a lump of arsenic. And so arsenic is sort of a really recognizable element, and we have a lot of associations with it. And I remember hearing an interview with a spokesperson for a chemical plant in Texas, I think, that was where there had been groundwater contamination downstream from the plant. And the spokesperson said, yeah, they've detected arsenic in the water, but arsenic is really a scare word, And on one hand, that is probably not the best public relations. To say, oh, it's arsenic, but arsenic is not that bad. But on the other hand, he has a point, which is that there are trace amounts of arsenic in just about everything. So all our food has a little bit of arsenic in it, a few parts per million or billion. And that's okay. And there could be a little bit more than that, and it's also okay. It's not going to be toxic. But on the other hand, this is a lump of arsenic, 1 part per lump, and it's and the reason that even though there is a little bit of arsenic in everything, the reason we have these associations for it is that in large enough quantities, it is toxic to virtually all known forms of life. And this is a lump about yay big is definitely a large enough quantity. So the phosphorus has the burning sulfur phosphorus and then the sulfur sitting on top of it. Next to it is the selenium and the bromine, which are also reacting pretty vigorously, although probably this one cloaked in the smoke that's bubbling off of the phosphorus here. And all of this is wrapped in this smoke that's boiling off, which is also smoke that's full of fluorine compounds. just to make things more exciting. And so you have all the burning chunks, arsenic combining with the phosphorus and making all these compounds that are arsenic something oxide, arsenic fluoride, and things that if you don't get away pretty quickly, you will be breathing in a bunch of stuff that could definitely kill you. So the right thing to do here is to run away very quickly and not keep building rows, which is what we're going to do. The fifth row I think of as sort of the foreshadowing row, because the fifth row is the place where we meet our first mildly radioactive element. We hit, and this is one that I have heard. So I memorized the periodic table. If you hadn't gathered from the Pokemon story, I was like not always the best at being social and finding other people who shared my interests. So one thing was I learned the periodic table from books, but did not talk to a lot of people about it. And so this is an element where it's sort of like the aluminium thing. I've always pronounced it technetium, but the few times I have heard someone else pronounce it, which I have, although come to think of it, I'm not sure why I had heard that. But I've also heard technetium, and that led me. I was wondering about that, but then I got distracted because I decided to look it up on Wikipedia, and then got diverted into reading the something like 10,000 word talk page argument over aluminum versus aluminium, and I got into like archive 7 of that, and then had totally forgotten what I was originally supposed to be doing. But this element, whichever one it is the first mildly radioactive one. Now, in this scenario, it would not kill you before the arsenic, the phosphorus, the smoke, the fluorine, and then also, again, the left side of the table here, which is like slightly less bad, but still bad, the potassium and the sodium. Those would all kill you first. The technetium or technetium is not radioactive enough to kill you. At least, I think you would have to cradle it to your body for a day or so, or if you managed to eat a chunk of it or wore it as a hat, that could give you a lethal dose. Hopefully they can add that to the material safety data sheet. Do not wear as hat. But the radiation itself would really not be the biggest problem you would be facing here. For that, we're going to go to the 6th row, because the 6th row contains astatine. It contains a lot of other things too. And I remember when I first saw this printed in the book, I was reading, I was flipping through, and I hit this article and I hit this illustration. It was like, oh hey, I stopped drawing all the smoke and stuff. I wonder why. Was that a mistake? I had the mercury should be flowing just like the bromine was. How come I just drew them sort of stationary like that? And then I remembered that this is the only chance we will have to see this table is the snapshot taken right at this moment. Because so plutonium is radioactive, and we use it. We use uranium in reactors where we trigger chain reactions in the uranium, and those chain reactions, the uranium undergoes fission, and because I can never figure out the verb form that I would use there to say where it fizzes. Nothing sounds right, so I'm just avoiding saying that. It undergoes fission. It splits into chunks, and that releases energy, which splits more of it and splits more of it. But it will also, if you have plutonium sitting there, it's radioactively decaying, and so it emits heat. And that is what we use to power a bunch of the long-term space probes. So the Curiosity rover has, and I really find this amusing for some reason, but they have a chunk of plutonium, which I think we've come very close to running out at this point and may be buying it from Russia. But so if you're an element collector, I know that there's someone out there who's selling it. If you can avoid all of the federal agents who will try to find you, if you Google, I did Google plutonium prices for this and then started thinking like, wait a minute. Well, I'm probably on that watch list already. I think someone asked me if any of my research got me in trouble, and as far as I know, like all of that Googling, like there was a question I answered where I was writing about the expensive things the most expensive thing you could put in a shoebox, and I've looked up prices of a bunch of hard drugs, and then realized my search history is now like how much does, you know, heroin cost? How much does LSD cost? Okay, but like on the street in this city, how much does it cost? Or what about this city? You know, trying to get like a real practical street price. But really the only thing that the only consequence I've ever suffered was there was an article I was writing a couple of months ago. And at one point I wanted to include a sample of the items in the collection of the Library of Congress and like what kinds of things they were on the whole. And it was sort of hard to get broad statistics of the kind I wanted. So I figured, oh, hey, I'll just randomly sample their collection and look at 100 items and see how many of them are books and how many of them are other things. And so I found they had a web API and like collection items had one number. And I was like, okay, the number it's not too many digits. It's probably not too sparse a space. I'll just start requesting random IDs. And then I parallelized that because that was going too slowly. And I found it was really hard to get good data. And so I was like ramping up the number of requests I was making, and then suddenly they stopped returning anything. And then I found that not only had the API blocked me, but the entire Library of Congress website was now redirecting me to like a 403. And in fact, everyone in my building was also redirected to 403. And I felt like, and that's totally fair because I was definitely spamming their API and like abusing it. But I also felt really bad about that because I guess it was sort of I have never been like kicked out of a library before. I felt like that was a line I had crossed. So I really wanted to apologize to them. That I just wanted to tell people about their cool collection, but sorry. But so the thing that really entertains me about plutonium is that, so like we power, you think of these sort of complicated reactors, but with plutonium electric generators, we're just using the fact that this thing gets really hot. We just like wrap it in things that will generate electricity from the heat and from the radiation that's being put off by this. But then we have the problem that it's a big chunk of plutonium and it's hot and it's radioactive. And so they put it out on a long stick and just hold it away from the rover. And so if you drive, you can see like on the Voyager probe, they've done the same thing. And so they've got this long scaffolding arm, and at the end there's a little thing that I always assumed was a scientific instrument, but now it's just a chunk of plutonium. And the Curiosity rover has the same thing. And this plutonium has a half-life of on the order of a century, which means that after a century or so, or whatever the specific half-life is, 80-something years, the heat and power output will drop in half. And so they've designed it to keep working until the voltage drops to a certain point. And so it can keep running for decades, assuming the other stuff holds up. But if you wanted to run something for longer than that, you would need something with a longer half-life. I did work out, by the way, the plutonium chunk that they're using on Curiosity. If you had a Nintendo GameCube and a TV hooked up to it, it would provide enough power for, I think, about 130 years of continuous play. So if you are stuck on Mars and you've managed to commandeer the Curiosity rover, if you have brought nothing except a GameCube and a TV, but the half-life of plutonium is just about right, because if it were much longer, that also means that it is less radioactive because it's taking longer for half of it to decay, which means it will be producing less power and less heat. And so you always try to find a balance. And this is also why nuclear contamination sites, when like a reactor melts down or something, the really nasty elements are the ones that have half-lives of about 30 years. Because the ones that have half-lives of a day or two are incredibly radioactive, but then they all decay and they're done. And so those are what, those will be the things that will give people lethal doses very, very quickly. And then the things that have really long half-lives, like, uranium 238, I think is like on the order of billions of years. So that stuff does not decay often enough to emit much energy. So the really bad stuff is the stuff that is like a 30-year half-life. So it will contaminate the area for a couple of decades, but also be short enough that it's emitting a lot of radiation. And plutonium is, again, about a century. So it emits all of that heat in about a century. So astatine, in its most stable form, has a half-life of 8 hours, which means that all of the energy emitted by the plutonium powering the Curiosity rover over the course of the next century, if it keeps running, is being emitted by our lump of acetylene in an afternoon. This is why no one has ever collected enough of a sample of acetylene to really look at it. Because any sample large enough to see with the naked eye would also like melt the naked eye and vaporize itself from its own heat. And this actually leads to a really funny situation. My favorite thing about looking up these elements is if you look under acetylene, there are all these great chemistry data tables, like the handbook of CRC handbook of chemistry, and that list all of the elements and like every conceivable property you could want. And actually during the street drug research, I remember I was trying to figure out the cocaine density or something like that, and found that they actually have a whole bunch of data on a bunch of these, but then there was, for some of the drugs, they have like mysteriously missing chunks. I didn't know if those were removed for some reason, if that's sensitive information, or if it's just no one else has really tried to figure out the physics of like a shoebox of LSD. But in the handbooks, if you look up acetylene, you'll find all its density and stuff and its various properties. But if you look at surface appearance, is a field they'll have where they'll say, is it shiny? Is it reddish? Is it matte? Is it, does it have a luster? Is it black? And acetylene will just have like a question mark, because there is no way, if you have a sample that's large enough to reflect light, the light that the acetylene is emitting will be brighter than whatever it is you're trying to illuminate it with. And so no one has ever, so they think, I think that I've read that the best guess is that it is probably black, but if you were able to illuminate it brightly enough to see, but it's also possible that it's shiny and kind of metallic looking. And that will probably be a mystery forever, because those are chunks of acetylene that are a collection of a bunch of molecules in one place. This would be a chunk of about 1 liter, which is more acetylene than has ever been made or exists in the world. And this lump of acetylene would promptly turn into a column of superheated steam by that heat that it's pouring out. But it will then, this column of superheated steam will continue pouring out that heat steadily for the next 8 hours, and then the next day for less than that. And this is so if someone were actually trying to do this table following these instructions, first of all, there's a legal disclaimer at the front of my book that they said you can make this kind of a joke, but definitely do put this in, about not doing this at home. And this is one where if somehow you were a bunch of people with both the resources to get a hold of some of these elements and yet like an environment that was like fostering really weird experiments in the building, and where you might be able to get away with doing something like that. The acetylene, the amount of acetylene that you would be using here is a quantity that maximizes the amount of paperwork you're going to have to face. Because if it were smaller, like 1 liter is enough that it will probably demolish the building that you're doing this in. And there are going to be a lot of people asking questions. For example, whoever owns the building or whoever was paying you to do something else when instead you were doing this. And do you still have 20% time? Is that? Well, I guess you've already seen all the Google searches I've done for plutonium suppliers. You can find that. But if you did this, there would be no way that if it were a smaller amount of energy coming from the acetylene, you might be able to cover it up. You could just if it was a well-built room and sealed away, and then you have charred walls, a lot of radioactivity, but you could in your 20% time discreetly work to clean that up, and maybe the news of what happened would not go much past your reach your immediate superiors. If it were a substantially larger chunk of acetylene, then there would be no one left to submit paperwork to. And that is what would happen with the 7th row. And so the 7th row, we're getting down into the elements that just have numbers, and they have not settled on names yet. When I was a kid and learning the periodic table and playing Pokemon and being really totally well adjusted and very, very, and because all the periodic tables I learned as little kids had like an extra line that ended halfway across, and I don't know if it's like a typographic thing, but I feel like it's very, very satisfying to have the nice square rounded off shape, and it gives me this weird urge to like sabotage particle physics experiments so they don't synthesize element 119 and ruin the really nice justification. But the reason that the elements are only being filled in right now is that they are very hard to produce and they are very short-lived. And so acetine, the reason it decays so violently and destroys the building you're in is that its half-life is only 8 hours. So it dumps all of that stored up radioactive energy in 8 hours. Some of the elements at the bottom of the periodic table will decay. They have half-lives. Some of them are measured in seconds and a couple of them in milliseconds. So all of the energy that's released by your column of heated astatine rising into the stratosphere over the course of an afternoon will be released by these elements like now, right away. It would be sort of like it's sort of like a nuclear chain reaction, only it's not it's not one part triggering. It's not one of them decays and that triggers the other ones to decay. It's not a chain in that sense. It's just a reaction. It all happens at once. And then, however, there is sort of a chain element because the elements that are way far up on the periodic table, some of them will emit a couple of protons and neutrons, which now makes element 118 has 118 protons. It decays immediately, releasing some protons, and becomes element, maybe it drops down 2 spaces. It becomes element 116, which is also extremely radioactive and has a very short half-life. And so you get these decay chains, all of them pouring out a whole bunch of more and more and more energy all at once. And the energy released, so if you were able to watch this whole scenario from very, very, very far away, on one of the mountains. Which way are the prevailing winds here? They come in from the ocean, so I guess from the west out over the east. So maybe to the south in the mountains, southwest. Anyway, you would first see this. Because the energy released in the first few seconds would be on the order of that from a medium-sized nuclear weapon. But because of these decay chains, these things are just continue decaying and decaying. So it's like a nuclear bomb which just keeps exploding. And what happens is you've got your wall which existed for if it's made out of 1 liter blocks, I guess it'll be a couple of meters wide. It will take light in the neighborhood of 10 nanoseconds to cross from one side of the wall to the other. So you have that much time to enjoy it before the radiation vaporizes it. But it vaporizes it, but you've still got all this plasma of these radioactive nuclei which are continuing to decay. So your mushroom cloud is now pouring out all these radioactive products and elements, and it's continuing to become super hot. The winds carry it away from you, cover everything downwind, and I only realized very, very recently that when you have a mushroom cloud and you have all the heavy dust and stuff with the uranium dust on it that is in the mushroom cloud, but it's heavier than air. So as it cools, it falls down from the cloud onto the ground, which is actually why it is called fallout, because it falls out of the mushroom cloud. And I guess that's sort of obvious in retrospect, but it had never occurred to me until just now. So this cloud, it's full of this stuff which falls out of it and covers land. And this stuff is rapidly decaying. All of these elements way down the table are decaying until they reach something so stable as astatine, and then they take a break. And that is a much more calm situation, because then it's just superheated plasma and not quite as superheated exotic particle mess. That's this whole mushroom cloud will continue spilling out this stuff as it goes downwind, rendering more and more areas uninhabitable for long periods of time. And from a nuclear cleanup point of view, it's sort of hard to figure out what to model this on because in a sense, you have, because of the ways the steam is superheated and it's all mixed in this cloud, and you've got a lot of heat and then a lot of cold environments and a lot of high pressure environments and then low pressure environments. And you have samples of literally every single element in this, at least at first. You have all of chemistry happening at once. Every different pair of atoms that can run into each other will be running into each other here somewhere in your cloud, and they will be doing it under every different kind of conditions. So every product that could happen from a reaction that you're like, oh, this is hard to clean up, will be happening in this cloud. You know, so in addition to all of the radioactivity and all of everything, like if you just flip through a chemistry book, you can point to like anything, you will have that problem to deal with too. And also, and at this point, it's definitely the least of your problems. But all I can think is also there's a liter of fluorine in there too. I just have my gas mask, and I'd be thinking about that too. So this, if nothing else, definitely it definitely helped me come to terms with my sort of Pokemon inspired frustration that you can only buy 85 or 90 of the 118 elements, because this has really driven home that the most important thing in element collecting is that you do not catch them all. But I got this, so I had made this, you know, I'd come up with a scenario, and I have a physics background, and in doing What If, I've sort of gotten a lot more into geology, as learning about, you know, the way continents break apart as you do various horrible things to them. That's been a lot of fun. And I've also learned a lot more biology lately, but I feel like chemistry has always been something that I've had a harder time with. Maybe just because there are a lot of things that you know, this atom is more electronegative than this atom, but like we don't have a real life. It's sort of harder to connect that to real life. And you know, quantum mechanics can be hard in the same way. And I really like stuff where it's easy to think about intuitively, like, you know, mass and speed and force. You know, that because, you know, you can think about like, this is an object, this is an apple. You know, this weighs this much. This is what a kilogram means. This is what a ton means. You know, and so I feel like I had a harder time with chemistry. And so after I finished this article, I got, because I was writing this for my book and had a little bit more luxury, you know, I can have a longer deadline, I got in touch with a professional chemist. And because I wanted to run it by him. I said, you know, here are all these reactions that, you know, that I've worked out that I think will happen, but I wanted you to look over it and let me know what you think. So and this guy, he was really helpful. It's I talked to Derek Lowe, who's a chemist who also writes the drug industry blog In the Pipeline, which I had read for a while. And so he you know, went through my article, and actually his first question was, you know, if you're going to build this, you know, this would definitely not be a good idea. He said, but so what form is the carbon in? Do I get to specify? Do I get it to be a giant chunk of diamond? And I said, I don't know. And he said, well, because, you know, diamond, it will actually burn if you get it hot enough. But that's pretty difficult. And you'd have sort of the problem, the same thing that happened with some of the Cold War era projects, which is if you have an explosion like this, that's this violent, the question is, will it fling the thing away before it delivers enough energy to disintegrate it? So he said there's a decent chance that when you have this radioactive, you know, nuclear bomb going off, that it's possible that the diamond will not be incinerated. So back in the early days of when we were still doing nuclear weapons tests, there was this series of tests underground. One of them was Operation Plum Bob, where they had a nuclear weapon going off in an underground chamber with a shaft connecting to the surface. And the shaft had like a cement plug and like an iron, like some kind of heavy steel cap on it, and you know, sort of blocking the top of it. And some of them have been doing some calculations about when you have the incredibly high pressures in this that have nowhere to go except up the shaft, they're going to hit this plug. And they think the plug will not actually be disintegrated by this, but it might be hurled away. And there was an interview with one of them where he talked about how they weren't sure how fast it was. They thought it was going to be flung away, and they were coming up with some sort of high numbers for the speed. And so what they did is they trained a high-speed camera about a quarter mile away on the mouth of the shaft, just to catch anything that happened. And so they detonated the bomb, and they had this high-speed camera. I think they said it was running around 300 frames a second. The plug that was over the top of the shaft appears in the air in one frame. So they can put a lower bound on how fast it was going, but they do not have an upper one. The lower bound is I tried to run through the calculations myself, and it's, it's hard, the field of view of the camera, it's a little bit tricky to calculate, but it is a double-digit number of kilometers per second. One of them came up with about 65 kilometers per second. And that's interesting because you'll see sometimes the Helios 2 probes that we sent around the sun are often listed as the fastest human objects, like the fastest thing we've ever made. And, sort of frame of reference questions, it's hard to figure out how to define that. But with reference to the sun, the thing that was going around, they dropped so close, they whipped around it really fast. And at the bottom of that, they got up to about, around 60 or 70 kilometers per second. But depending on exactly how fast this manhole cover that was on top of this thing was going, it is possible that for a moment, this was the fastest object ever built. And there was some thought that this might have, because if it was going at 60 kilometers a second, the escape velocity from the surface of the Earth is less than 10 kilometers per second. So, and in fact, the escape velocity from the whole solar system from where we are is only about 40 kilometers per second. And so this manhole cover, which was never found, may have left. It's possible, given its speed, if it made it out of the atmosphere. And I actually started doing a bunch of calculations to figure out if it was going forward from the Earth, like in the direction of the Earth's motion. If they were pointed toward the direction the Earth was going, you get to add on the Earth's 30 kilometers a second speed around the sun when you're trying to get up to the escape velocity. And so this thing could be going over, 100 kilometers a second, which would send it straight out of the solar system. And it would be going way, way faster, even after it had lost all its speed there, than the Voyager probes at their fastest. And so that would now be our first representative heading toward the stars, which is a really appealing idea. And what I came up, I think I came up with it was like digging through these files, trying to find what time of day did this happen, which way would the shaft have been pointed? And I think that it came out, the Earth's speed came out as kind of a wash. But it's also, it's sort of a moot point because the sort of, if you do some further calculations, show that probably the manhole cover, because it was not quite large enough, probably did not survive the impact with the atmosphere. So it would have been sort of the only time in Earth's history that we've seen a meteor going directly upward, burning up in a plasma trail, and so probably that manhole cover was destroyed, but it's possible it is still out there somewhere. So when I talked to the chemist, his first question was, "Hey, that chunk of diamond, it's possible that's just going to be flung free from this explosion and have landed okay." And then at the very least, I would like to go and pick it up and then use it to pay for all of the damage that I did to the labs and to the city and all the rebuilding, and then he thought for a second. He was like, "I would definitely wipe it off first, though." But he also, what was
We can raise the handlebars. We can change the seat. I'm going to talk to you about some stuff that's in this book of mine that I hope will resonate with other things that you've already heard, and I'll try to make some connections myself in case you missed them. I want to start with what I call the official dogma. The official dogma of what? The official dogma of all Western industrial societies. And the official dogma runs like this. If we are interested in maximizing the welfare of our citizens, the way to do that is to maximize individual freedom. The reason for this is both that freedom is in and of itself good, valuable, worthwhile, essential to being human, and because if people have freedom, then each of us can act on our own to do the things that will maximize our welfare, and no one has to decide on our behalf. The way to maximize freedom is to maximize choice. The more choice people have, the more freedom they have, and the more freedom they have, the more welfare they have. This, I think, is so deeply embedded in the water supply that it wouldn't occur to anyone to question it. And it's also deeply embedded in our lives. I'll give you some examples of what modern progress has made possible for us. This is my supermarket, not such a big one. I want to say just a word about salad dressing. 175 salad dressings in my supermarket. If you don't count the 10 extra virgin olive oils and 12 balsamic vinegars you could buy to make a very large number of your own salad dressings in the off chance that none of the 175 the store has on offer suits you. So this is what the supermarket is like. And then you go to the consumer electronics store to set up a stereo system, speakers, CD player, tape player, tuner, amplifier, and in this one single consumer electronics store, there are that many stereo systems. We can construct 6.5 million different stereo systems out of the components that are on offer in one store. You got to admit that's a lot of choice. In other domains, the world of communications, there was a time when I was a boy when you could get any kind of telephone service you wanted as long as it came from Ma Bell. You rented your phone, you didn't buy it. One consequence of that, by the way, is that the phone never broke. And those days are gone. We now have an almost unlimited variety of phones, especially in the world of cell phones. These are cell phones of the future. My favorite is the middle one, the MP3 player, nose hair trimmer, and creme brulee torch. And if by some chance you haven't seen that in your store yet, you can rest assured that one day soon you will. And what this does is it leads people to walk into their stores asking this question. And do you know what the answer to this question now is? The answer is no. It is not possible to buy a cell phone that doesn't do too much. So in other aspects of life that are much more significant than buying things, the same explosion of choice is true. Healthcare. It is no longer the case in the United States that you go to the doctor and the doctor tells you what to do. Instead, you go to the doctor and the doctor tells you, well, we could do A or we could do B. A has these benefits and these risks. B has these benefits and these risks. What do you want to do? And you say, Doc, what should I do? And the doc says, A has these benefits and risks, and B has these benefits and risks. What do you want to do? And you say, if you were me, Doc, what would you do? And the doc says, but I'm not you. And the result is we call it patient autonomy, which makes it sound like a good thing. But what it really is a shifting of the burden and the responsibility for decision-making from somebody who knows something, namely the doctor, to somebody who knows nothing and is almost certainly sick and thus not in the best shape to be making decisions, namely the patient. There's enormous marketing of prescription drugs to people like you and me, which if you think about it, makes no sense at all since we can't buy them. Why do they market to us if we can't buy them? The answer is that they expect us to call our doctors the next morning and ask for our prescriptions to be changed. Something as dramatic as our identity is now become a matter of choice, as this slide is meant to indicate. We don't inherit an identity, we get to invent it, and we get to reinvent ourselves as often as we like. And that means that every day when you wake up in the morning, you have to decide what kind of person you want to be. With respect to marriage and family, there was a time when the default assumption that almost everyone had is that you got married as soon as you could, and then you started having kids as soon as you could. The only real choice was who, not when, and not what you did after. Nowadays, everything is very much up for grabs. I teach wonderfully intelligent students, and I assign 20% less work than I used to, and it's not because they're less smart, and it's not because they're less diligent. It's because they are preoccupied, asking themselves, should I get married or not? Should I get married now? Should I get married later? Should I have kids first or a career first? All of these are consuming questions, and they're going to answer these questions whether or not it means not doing all the work I assign and not getting a good grade in my courses. And indeed, they should. These are important questions to answer. Work. We are blessed, as Carl was pointing out, with the technology that enables us to work every minute of every day from any place on the planet, except the Randolph Hotel. There is one corner, by the way, that I'm not going to tell anybody about where the Wi-Fi works. I'm not telling you about it because I want to use it. So what this means, this incredible freedom of choice we have with respect to work, is that we have to make a decision again and again and again about whether we should or shouldn't be working. We can go to watch our kid play soccer, and we have our cell phone on one hip and our BlackBerry on our other hip and our laptop presumably on our laps. And even if they're all shut off, every minute that we're watching our kid mutilate a soccer game, we are also asking ourselves, should I answer this cell phone call? Should I respond to this email? Should I draft this letter? And even if the answer to the question is no, it's certainly going to make the experience of your kid's soccer game very different than it would have been. So everywhere we look, big things and small things, material things and lifestyle things, life is a matter of choice. And the world we used to live in looked like this. That is to say, there were some choices, but not everything was a matter of choice. And the world we now live in looks like this. And the question is this good news or bad news? And the answer is yes. We all know what's good about it, so I'm going to talk about what's bad about it. All of this choice has two effects.